This is the first lecture for Module 2 of Unit 2. Module 2 concerns miscibility, ideal, and ideally dilute solutions. This lecture, the first part, Part A, concerns miscibility and ideal solutions. Miscibility is about, or a question of, will things mix, or will solute B dissolve into solvent A to make one liquid solution. Solutions form when species have similar attract forces. This rule is called like dissolves like, and is another reason it is important to understand attractive forces. In general, solvents may be classified as polar, for polar molecules, or nonpolar, those made up of nonpolar molecules. In general, polar solute molecules will be attracted to polar solvent molecules, and polar molecules will form solutions of polar molecules. Likewise, the attractive forces between nonpolar solute and solvent molecules are similar, and so solutions of nonpolar species will form. In general, we've seen that ions dissolve readily in water, a very polar solvent. This is because ions are themselves quantities, while not with positive and negative charges, which interact with the polar solvent molecules. So, for example, carbon tetrachloride will dissolve iodine because carbon tetrachloride is a nonpolar molecule and iodine is a nonpolar molecule. But carbon tetrachloride, being a nonpolar species, will not dissolve the ionic compound potassium chloride. Alright, considering three species, lithium chloride, benzoic acid, and naphthalene, which will be most soluble and which will be least soluble in water? Naturally, molecules we're dealing with are important here, so it is important to know that naphthalene is a molecule made entirely of carbon and hydrogen atoms. The answer is that the ionic compound is expected to be most soluble. Benzoic acid, which may experience polar bonds in the form of hydrogen bonding, will be the next most soluble. And naphthalene, which is a nonpolar species, might not be expected to dissolve in polar water molecules at all. So, lithium chloride will break into charged particles which will interact with polar water molecules. You've seen that in previous chem courses. Benzoic acid may well form hydrogen bonds with the water molecules. Water molecules would like to react with other water molecules other than naphthalene. And the naphthalene nonpolar naphthalene molecules may not be able to push their way in between the polar water molecules at all. The role of these intermolecular forces of solute and solvent often appear in heat of solution. If attractions of A molecules for itself are greater than AB, the heat of solution is greater than zero and a solution may not form. As the naphthalene water example we've just discussed, water is more attracted to itself than to nonpolar naphthalene molecules. If AA attractions are less than AB, then attractions between A and B are such that the heat of solution will be less than zero. we might expect a solution to form under these circumstances. Solutions mixed readily when there are similar forces of attraction between A and B. These heat solutions with heat of solution equal to 0 are called ideal solutions. Vapor pressure of ideal solutions is relatively straightforward to determine and is an often seen property of ideal solutions. Total pressure of an ideal solution is the vapor pressure of pure A times the mole fraction of A plus the vapor pressure of B times the mole fraction of B. Mole fraction of anything, mole fraction of A, is equal to the moles of A over the total moles. So in this case, it would be equal to moles of A over moles of A plus B. P star A is the vapor pressure of pure A. So, which of course is a constant at a given temperature. So consider we mix equal masses of heptane and pentane. Vapor pressure of heptane is 36 and pentane is 420 torr. What is the vapor pressure of the solution? You should attempt this straightforward example before continuing. To make the problem of equal masses easy to solve, let's assume 100 grams of pentane and 100 grams of heptane, and then find moles and mole fractions of the two species. Pentane molecules have the formula C5H12. We can convert grams to moles, 1.386 moles of pentane. Likewise, we can look up the formula for heptane quickly, and we can convert grams of heptane to moles, and we have moles of each. We have total moles is the sum of the moles of each, 2.3840. Then we can quickly find moles of pentane by dividing moles of pentane over total moles. You dealt with mole fractions of gases before when dealing with ideal gases. You may remember that all mole fractions in a mixture add up to 1. So we can obtain the mole fraction of heptane simply by taking 1 and subtracting the mole fraction of hexane, or rather pentane. We end up with a mole fraction of 0.58138 for pentane and 0.48162 for heptane. Common arithmetic or mistake at this point for this sort of problem, often made by beginning students, is to use moles instead of mole fractions. Be sure to obtain mole fractions before moving on to apply the equation we had seen on the previous page, which is known as Raoults Law. We can let pentane be A and heptane be B, and then calculate the total pressure of solution by finding pressure of pentane times mole fraction of pentane plus pressure of heptane times mole fraction of hexane. The answer is 259.1 torr. Interesting points. Notice that this mixture is between the vapor pressure of pure pentane and the vapor pressure of pure heptane. Notice heptane, a larger molecule with more London forces between molecules, has a lower vapor pressure than pentane. And notice that these molecules, being made up of carbon and hydrogen, are nonpolar molecules. And so we might expect that a solution of these two molecules with similar attractive forces would behave like an ideal solution. Ethylene glycol, or antifreeze, is added to solutions of water in the radiators of automobiles. The reasons for this will be discussed further in the third module of this unit. But since ethylene glycol is a polar molecule, which may engage in hydrogen bonding, we see from its structure, it has similar enough attractive forces to water that we could sort of approximate antifreeze water solutions as ideal solutions. Since ethylene glycol has two OH groups on it, and is in addition a larger molecule than water, the vapor pressure of ethylene glycol is very small. We'll call it 0 for our purposes in this case. Meanwhile, at 25 Celsius, vapor pressure of water is 17.5 torr. Right. Assuming that these two polar species, hydrogen bonding species, form an ideal solution, what is the vapor pressure of a solution that is 20% glycol by mass? Attempt before continuing. Right. Again, the problem becomes easier if we assume 100 grams of solution. Then we have, because we know the mass percentage of the solution, 20 grams of ethylene glycol and 80 grams of water. Convert both of these masses to moles using the molar mass of ethylene glycol. 20 grams of ethylene glycol divided by the molar mass is 0.34 moles. 80 grams of water divided by the molar mass is 4.4 moles. Actually, allow me to clear up an arithmetic error there. The molar mass of ethylene glycol is around 62 grams. So we have 0.32 moles of glycol and 4.4 moles of water. Total moles is then 0.3 moles plus 0.44 moles is 4.7 moles. Mole fraction of water is 0.94. When we solve for the vapor pressure, we include only the vapor pressure of water times the mole fraction of water. We do not need to include a term for the glycol because its vapor pressure is 0. The answer is 16 torr. By adding glycol to water, we lower the vapor pressure from 17.5 to 16.